Have you ever asked an AI to just reword a quick email? It feels like magic, right? Instant, totally digital, almost weightless. But what's really wild is that behind that simple little prompt is a massive, very real, very physical process. So let's pull back the curtain and see what's actually happening.
Seriously, every single time you hit enter, you are kicking off this huge chain reaction. It's happening in a giant data center, maybe hundreds or even thousands of miles away. So what is the actual physical price we're all paying for that convenience?
Well, let's just start with the scale because it's kind of mind-blowing. OpenAI alone says it gets about 2.5 billion with a B queries every single day. And no, that is not a typo. We're talking 2.5 billion requests that all need to be processed, computed, and this is the important part, cooled down. Okay, so when you add up all of those queries every single day, the cost is just staggering. You're looking at enough fresh water to supply a whole city. And the energy drain? It's like binge-watching Netflix for over 3,000 years. And remember, that happens every single day. And all of this brings us to the fundamental problem, the big challenge that every one of these AI data centers is facing. It really all boils down to one thing: heat. And to keep these super powerful computer servers from literally cooking themselves, they have to make a choice, a huge trade-off between two of our most vital resources.
Yeah, and we are not talking about some dusty server room in the back of an office. The crazy demand from AI has basically created this whole new class of building, the hyperscale data center. I mean, these things are absolutely enormous, sometimes more than 13 times the size of a traditional data center, just packed to the gills with servers, all generating an insane amount of heat.
So you've got two main ways to cool them. On one hand, you've got evaporative cooling, which is what Google does up in Oregon. It's way more energy efficient, sure, but it guzzles just a staggering amount of fresh water. On the other hand, in really dry places like Arizona, they use air cooling. That doesn't use any water on site, which is great, but it needs a ridiculous amount of electricity to power these giant fans. It's a classic environmental catch-22, right? It's like Professor Scanlon from the University of Wisconsin said. We've had data centers around for decades, and for the most part, we never even noticed them. But the sheer size and just the appetite for resources of these new AI-driven centers, well, that's something we've never, ever seen before.
Get this. In a lot of traditional data centers, almost half of all the electricity they suck down isn't even for computing your prompts. Nope, it's going directly to the cooling systems, the fans, the AC, just to keep the whole operation from melting down.
So you can probably see where this is going. This kind of brute force approach just isn't sustainable. As AI models get more and more powerful, they're just going to generate even more heat. So the industry is finally realizing it can't just work harder, it has to start working smarter.
One of the first really big innovations is something called direct-to-chip cooling. So instead of trying to air condition an entire warehouse-sized room, this method targets the heat right where it's being made. You've got this liquid coolant running through a sealed loop right over the microchips themselves, pulling the heat away super efficiently. And the best part? It uses no on-site water.
Okay, so that's already a huge leap forward, but what if you could take that idea to its most extreme kind of logical conclusion? What if you could just submerge the entire thing?
Well, it's called immersion cooling, and the results are just wow. By literally dunking the servers in a special non-conductive liquid, you get rid of the need for fans completely. Some companies are reporting that over 97% of their energy goes directly to computing. Now, compare that to the 50% we were just talking about. It's a total game changer. And with that kind of incredible efficiency gain, you've got engineers and researchers starting to look at even more radical, almost sci-fi locations to put these things, really pushing the boundaries of what anyone thought was possible. So one of the most promising ideas right now is to just put them underwater. By using the natural, free cold of the deep ocean, some companies have seen around a 40% reduction in both the power they use and in their carbon emissions. It's like Maxie Reynolds from Subsea Cloud explains it. The ocean itself basically becomes the heat sink. You don't need any electricity for cooling, and that means pretty much all the power, like 99% of it, can be dedicated just to computation. But you knew there was a but coming, right? Of course there's a catch. What happens when something breaks? Researchers will tell you hardware like GPUs, they fail all the time. On land, that's a pretty easy fix. But when your data center is sitting at the bottom of the ocean, yeah, maintenance becomes this incredibly difficult and very, very expensive problem. Okay, so if underwater is tricky,
what about going up? The idea here is to launch data centers into orbit. You'd use solar panels for basically infinite power and the cold, empty vacuum of space for cooling. Sounds perfect, right? Well, not so fast. As any astronomer will tell you, it's not that simple. Without any air to carry the heat away, an object sitting in direct sunlight can bake at up to 120 degrees Celsius. So these futuristic solutions are fascinating to think about, but let's be honest, they're still a ways off. So while some folks are looking to the stars, others are focused on a much more immediate goal. What if we could just reduce the need for all that cooling in the first place? And this is where software and just smart strategy come into play. We could shift computing jobs to run at night when it's naturally cooler, or maybe move them to regions that have more water. We can actually train AI models on smaller, more efficient datasets. And even we, as users, can make a difference by choosing less resource-hungry models for simple tasks. It's not just about bigger, crazier hardware. It's about smarter software.
So I guess the real takeaway here is this. AI isn't just some code floating around in the cloud. It's a physical industry. It has very real, very tangible demands on our planet's water, on our energy grids, and on the actual human communities where these giant facilities get built.
And that really leaves us with one final critical question. As our reliance on this technology just continues to explode, we're going to have to decide how we're going to manage its very real environmental costs. And maybe more importantly, who is ultimately going to be responsible for paying that bill?